Hello. So this is Mikhail. Just decided to record an overview of the GitLab Agent repository to help anyone who is interested understand how things work and hopefully contribute. So let's start with packages. I don't have a specific plan, but let's start with packages. So top level packages and directories and files. Obviously, this is, you know what it is. Then it's for Bazel, all the temporary directories and files, that ignore them for now. Then we have the most important packages here, which are CMD, internal, and PKG. And let's talk later about the other ones. So CMD is a convention that is very widespread in Go. CMD stands for commands, so binaries that your repository produces. And we have two binaries here, agent K and Kubernetes Agent server class, and some additional files here that are shared by these two packages. Then we have internal and PKG. So these are conventionally named packages as well. Internal contains implementation details, packages that should not be depended upon by anything else that imports this project to, to use some code. And PKG is the opposite, which is packages that, it's okay to depend on them, and perhaps the author of the repository provides some guarantees, semantic versioning and anything like that, like stability guarantees about that. So here we have two packages which are configuration for the agent, which is what you see in the configuration repository, and configuration for CAS, which is a configuration file that is just a file that CAS can read to get its configuration from. Both define the structure using protobuf, and let's, I guess, start with this one. So the configuration is described using the top level agent configuration message, and then it like drills down into the lowest levels here with IDs and everything. So name is just a way to specify the name in JSON encoding for the field. That's nothing really interesting here. And then there's this one, which is CAS configuration, as I said. Also, I try to maintain commands here as documentation. And there's also nothing really interesting here. Maybe one thing is we are using a standard well-known types. That's how they are called. Standard type from type repository, I guess, of protobuf. So this is a duration type, and it comes from standard place. Magical import from Google protobuf. Also here, well, that's it basically here. Well, let's go into, and IT's integration test, which is not really working at the moment, just scaffolding basically for it. I've started but never finished. And the doc is documentation, obviously. Then build is various things for the build, as the name implies, and deployment is deployment for the agent K. It contains a KPT package, documentation is here, and customize layers based in cluster. Okay. Other files here, like nothing really interesting, I guess. this is for Bazel as well, and this is for Bazel. We'll talk about Bazel in the end of this video, I think. Let's focus on how things work in general. So, as I said, I guess we can start from the commands, right? So we have agent K and CAS, and when the interaction is defined, so they talk to each other using gRPC, and the interaction is defined here in this directory. We have a protofile which describes the messages and, most importantly, the service. This is the service that CAS exposes, and it's meant to be used by agent K. So there are two methods right now, two RPCs. The first one is the first one that agent K calls when it starts, and it's to fetch the configuration, and it just sends an empty request and gets a stream of responses. So each response contains configuration for the agent, and this comes from the repository that is mapped to this agent. The mapping is stored in the database, so the agent sends the token. Using the token, we look up the agent record. Using the record, we look up the project, and from that project, we know which GitLab stores the data, and we talk to GitLab and fetch the file, configuration file. Then we send the configuration file back to agent K. Agent K parses it and handles the configuration. This is how configuration is flowing. And an interesting thing here, at least it was for me, is also importing the types from another protofile. And you see, this is an internal proto package, proto file, you know, package, proto file. And we import a public configuration, which is defined here in this protofile. So agent configuration, if we click, it moves us to this package and type message. Okay, then the second method that that agent K calls is if in the agent configuration, let's go there, we have deployments. It's a list of repeated means it's a list or array, you know, a slice in Go, an array of manifest projects. Each is an ID of the project, something like that. And so agent K starts invokes this method to get objects for this repository. So for each repository, it starts a separate Go routine, and that Go routine is responsible for fetching the objects and synchronizing them with the cluster where agent K is running. So as you can see, well, this is the request, which is just the project ID. So it takes it from configuration from here, and it sends it to CAS, and then CAS responds with the stream of objects to synchronize, which is the commit ID, and again, an array of objects, and each object is the YAML that is stored in some file. This is just the name of a file for error messages. If there is an error, parsing the file, what file was it, you know? And this is just YAML, bytes of YAML that we parse. And currently we only support one file, but we will support like traversing directories and at least multiple files in the directory. That's why it's a array as well. Repeated means multiple, as I said. And it's a stream like here as well, because agent K keeps the connections open, and CAS sends updates when they happen. So CAS is what is doing polling. CAS is what's polling GitLab. for both of the open connections. And when there are updates, a new commit is detected, then it, handles that and sends the update back. For configuration of new objects in the repository. So if there is nothing that is happening, then there is no traffic, or except for keep alive messages maybe. But there is no polling that the agent is doing. So this is very optimal, I think. Polling is happening close to the source where the changes are. So this is where this proto file is where the interaction is defined. Yeah, there are only 2 methods at the moment. We'll have more sometime in the future. Okay, then I guess let's go back and see what else is here. So for proto files, we have generated code, and this is just proto compiler for Go generates representation of the messages and RPCs for the proto file. Okay, I think we can go and look at the. Okay, maybe a few more things here. So internal agent K is the sources of the agent, apart from some bootstrapping code that is here, and agent RPC is what I just showed you, which is the gRPC definition, and API is just various API definitions for types and structs and stuff that is like globally used. Information about the agent, and information about the GitLab instance, and information about the agent that is returned by the GitLab when Cas asks about it, and information about the GitOps project that we fetch from GitLab as well. Here we are importing a type from GitLab, which this type describes a Git repository basically. So it contains all the information that GitLab needs to, wow, that's a lot of stuff, right? All the information GitLab needs to find the repository on disk, and anything else basically that is needed. We just pass it through. This is API, and this is client for GitLab. This is client for GitLab. This is sources for Cas, the server. This is just various helpers, tools, and stuff. Testing and for tunneling binary streams through a WebSocket connection, basically. This uses a library, but also I've done some nice helpers to simplify usage. Okay, this is probably it for internal. Let's start with, we haven't looked at any code yet, so let's try doing that. So this is, I think it makes sense to start with commands. So agent K is, as I said, agent K, the thing that's running in the cluster. So that's what it does. This is just reusable stuff that is coming from here. CMD is the name of this package, and you can see it in the imports. Unlike Ruby, there's no magic. You can easily find where things are. So this is CMD, you can just click, and you definitely are going to the right place in your sources or in libraries. And yeah, it's just plumbing to start the program properly, seed the random number generator, start it, and exit if there was an error with an error code. And then this sets up command flag parsing, and this sets up sig term and sig int handling. So if GDK, let's say, sends us a sig term, we will stop well, not for cast, but not for agent K, but for cast. This is the same code. And just various plumbing, nothing interesting. Then this is like a factory that produces something that is runnable, and this starts the application for agent K. We're looking at agent K. So here we just define command line flags. This is coming from Kubernetes libraries to bind command line flags, and then we parse them and so on. And this is all just set up. Reading the tokens, credentials, establishing the CAS connection. That's really nothing very interesting, but the main thing here is we are configuring the CAS connection. This is the most interesting thing, which is happening here, and we are doing the dial, gRPC dial, and then we are passing this connection to agent K. This is the place where the logic lives, and it's in the internal. So it is internal agent K. This is the implementation of the agent. So we have CMD agent K and then internal agent K. See, just to repeat, CMD is the binary, and we have the bootstrapping kind of code here that constructs the connections, parses flags and so on. That's what it is. But the logic is here in internal. I like to structure programs like that, where you have main, which is the entry point, and then you have the non-main, where everything else, all the logic lives, bootstrapping logic, not all the logic, but bootstrapping logic, and then it bootstraps something that is not here, but is a separate type. So agent K, the agent, separate type, which doesn't know where the client is coming from, the engine, GitOps engine factory, where it's coming from, how it works, and how to access Kubernetes. It just has interfaces, and this is where the business logic basically lives, right? And this structure makes it easy to unit test everything. So you can inject mocks and just test the business logic without having a real CAS running, using a real GitOps engine or using a real Kubernetes connection. So also for this approach is also for unit testing, and I use it a lot here in tests. Okay, so when the agent is started, it starts polling the refresh configuration endpoint, the one that's defined here, right? Get configuration. So this is just an infinite loop until we get a signal that we should stop, and we call this method every 10 seconds. And this method is a loop itself, has a loop itself. So this is, as you can see, get configuration. We are calling it on the CAS client, and then we are consuming the response stream here and applying the configuration that CAS sent. And this configuration starts workers to do GitOps, but that's too detailed, I guess. I'm not sure how deep we should go. Let's start with just overview of how things work. So this is the configuration refresh. Then each worker for GitOps has a separate loop here, which is where it's calling get objects to synchronize. This is the loop that is consuming the stream from the server. So if the connection breaks, this method exits, but then because we also use it in a loop, so we poll, but polls are very rare, because typically you connect and you do not disconnect, but then if you disconnect for some reason, we retry the connection every 10 seconds. This is how Agent K interacts with CAS, these two APIs. And if we, I don't want to go deeper because there's a lot of logic and how things are handled, but that's not really important. I want to just show the high level building blocks. So let's look at CAS. CAS, well, let's start with command again. CAS has an identical structure, a main that's also using the same plumbing, and then new from flags also binds various flags. Ideally, we want to drop all the flags except for this one, which reads the configuration from the file. Then we read the configuration from the file. We apply, load configuration for file, apply defaults to configuration, then also apply configuration from flags. That's why I want to drop it, because then I can delete this. And then we create this implementation of CAS, which lives here as well in the CMD. This is, so we have a bootstrapping thing that parses the flags and configuration, and we have the options, which is the options that CAS should work with, and it just contains the configuration file contents, basically contains the contents. Okay, and it's got run method, which is what starts the real CAS, and it uses the configuration to start the network listener, to establish connection to GitLab and GitLab client, that it constructs all the things from the options. And then this is where we construct the real CAS, the server. Again, as you can see, we inject all the clients, and so GitLab pool, something that pulls the connections to various GitLab servers, the GitLab client, and various configuration parameters. And then this is the server. Then we register the server with the gRPC server, and gRPC server is what starts listening on the network socket for connections. Okay, then this is all, again, bootstrapping. The main logic lives here in PKG, in internal CAS, not PKG, internal CAS, and this is the, as you can see, interfaces and some parameters and some internal field metrics. Then it started using the run method, which is just sends the usage ping information. And the interesting things here is server struct implements an interface. We can go back to the definition of the interface that it implements. And this is the generated, you see, agent RPC protobuf Go. This is a generated file. It says that it's a generated file. So this is the interface that our server implements, and it's the gRPC server that calls these methods on our server. This is how we implement the API, basically. This is what is called when agent K wants configuration, then another one. This is when it wants objects for GitOps. This is the structure of things. Okay, yeah, let's not go into the low level details. I think this is probably a good overview, but let's talk about what else do we have. Let's see what else we can talk about. And we have the GitLab client, GitLab client. It's just nothing really interesting. But yeah, let's, I guess, talk about make file, because this is what you will use to run tests and so on. So if you make changes, you can just run make test, and the test is defined here. It formats everything using Go imports, generates the build updates and generates the build files for Bazel and runs the tests. Test CI because CI runs this job. And this is what we run to run all the unit tests and build all the packages. So Bazel test not on the runs tests, it also builds all the packages. And this means all basically. And then we also build the integration test. We don't build it. It's we don't run the test here. So apart from test, you may also want to run the linter. That's obvious. And then regenerate proto regenerates protobuf, regenerates generated code for the proto definitions. So this is this file. So if you make any changes to proto files, any of them run this task, it will run this Bazel target to generate and extract the files to put them here. Okay, what else is it? So we also have mocks, which we generate using Go mock. It's a library that can generate a mock using an interface, given an interface. So we generate quite a few mocks for several things. And these are the mocks that we use to test the business logic. We inject them in tests. And yeah, we use Go generate to run commands in each of the directories. Let's go and look. Let's, for example, go into this. Agent RPC mock. So we have the doc file, which defines the go generate command, and go generate actually does the go run. So go generate delegates to go run, which builds this binary and runs it. It's like a Russian doll, and we tell it to generate mocks into this file and use and generate mocks for these interfaces, and that's what we get. Mocks for CAS client and so on. And we have mocks for GitLab client, GitLab pool, sorry, GitLab client, GitLab pool, GitLab client basically, and GitOps engine, and for GitLab, that's another GitLab thing, and for all the RPCs, the interfaces to do gRPC, we also mock them, generate mocks for them so that we can test business logic in CAS and Agent K. And to regenerate them, yeah, the regenerate mocks command can be used. Then there's various plumbing for the builds. I guess let's just talk about Bazel a little bit. So you can think of a build as a graph of actions that the build tool needs to perform to produce a result. So when you do this, let's say you tell Bazel that you want this output. This string is called a label. This is basically directories and a label of a target in this directory. So here we want to build a Docker container for Agent K and a Docker container for CAS in this invocation. So if you think about, imagine a graph of what needs to be done, and you tell Bazel, I want these two vertices of the graph, and anything that these vertices depend on gets built basically recursively. It's like a depth first search, but also maybe handling the vertices, concurrently for parallelism to speed up the builds. So basically let's actually find this. It's in CMD, Agent K, container race is here. except that it's not, but this is the macro that generates this target, agent K. So we can, it's defined here. And we know that it's defined in this file because that's where it's coming from. Again, no magic. We just define the file, cmd Bazel. And it's just, we define the same targets for CAS and agent K. That's why I use a macro here. And we define binaries. So normal binary, binary with race detector on, binary that is built for Linux MD64 and the same Linux, but also with race detector. And then we define Go image is a Docker image with a Go binary in it. That's what it is. It uses rules Docker to package, to download the base image, and then use the binary that is defined here, underscore Linux is this binary. So we will package an MD64 Linux binary into a container here, basically. That's what it does. And it's called the container. So when we want container race, so it's the next one. This one is the Linux binary with race detector on. So if we ask Bazel to build these targets, it will, build all the whole graph that they depend on. And this is basically the idea behind Bazel, to represent the build as a graph. Then it also gives us, well, the build is composed of reusable libraries that that's what we use here. Like to build Docker images, we use this library. To build Go, we use this library. So unlike make or any shell scripts, you don't get low-level tools. You get reusable rules which you can compose and do, what you need to do. So it gives you some uniformity instead of just a free-form scripting environment. And because it's more constrained, it can ensure that the build is correct and reproducible. And because of that, it can also ensure that it can be incremental and correct at the same time. With Make, you basically cannot have incremental correct builds because Make assumes that it relies on timestamps. And if you check out a node, a branch, you have to do a make clean and delete all the build files because they are newer than your sources, but then they don't correspond to your sources because you have checked out an older branch. So you need to rebuild them. Make will not notice that. Okay, so Bazel doesn't have this problem. Here we define push targets. So to push the container, which is this thing, right? Name identifies the target. So name container, we refer to it here using the name. And we say it should be in Docker format when we push it and where to push it, target, and the registry and so on. All these parameters, they're kind of more or less obvious, but all of that is really well documented in the Rose Docker repository on GitHub. And we have a lot of targets because we have a lot of different images, and we have make targets for them. So this is the release when we want to release images for a tag in CI. We build all of them and then we run all of them one by one to push the image. And then this is a similar thing, but different targets for a commit. So if in a branch build you want to build the images, there is a manual task which you can manually run to get images for this particular commit. And then there is the latest, which runs on master to update the latest image. And This is for version, I think, when there is a version. Yeah, I don't remember why it's here. What it's for, I forgot. It's used somewhere. Oh no, it's not. Okay, it's not used because it's just here because you may want to run it locally from your computer. That's what it is for. And these ones are for CI to release everything, and these ones are to manually build an image and push it, and then you can use it. This is just for testing. And this target is for GDK. It's used from GDK to build CAS and copy the build CAS binary into this directory. Okay, is it all? Yes, I think this is it. All the targets in the makefile. As you can see, all the targets are phony targets, and that means we are not relying on makes, incrementality. We just use makefile as a file to store shortcuts to invoke Bazel, because it can be quite verbose, and it's convenient to just store things here. Okay, I think this is already probably too long. So thank you for the attention.